Let's use induction to prove the following identity, that the sum of the first n integers has the closed form n times n plus 1 over 2 for all positive integers. Okay, so the first step for doing an induction proof is the base step. So we first need to do the base step, which is to check for n equal to 1. So for n equal to 1, the left hand side is going to be equal to 1, because it's just going to be the sum of the first n integer is just going to be 1. And then the right hand side is going to be 1 times 1 plus 1 over 2. And this is just equal to 2 over 2, which is 1. So it's true. It holds for the base case. So the formula is true for n equal to 1. Now we need to do the inductive step. So now we need to show, so let me write here, we need to do the inductive step. And so what is the inductive step? The inductive step, we're going to assume true for n equal to k. And so what does this mean? So this means that we're going to assume that this is true for k. So when you sum all the numbers up to k, you get k plus 1 over 2. And now we need to show that it's true for n equal to k plus 1. And so remember, the idea is that if something is true for the number 1, and if something is true, or when something is true for one number, it's true for the next, then since it's true for 1, it's true for 2, it's true for 3, it's true for 4, and so on. And so it'll be true for all the positive integers. So now let's do this then. So if we take now the left hand side that we want to show, so 1 plus 2 plus all the way up to k plus 1. So we want to show that this will have the closed formula like this for n equal to k plus 1. And what we are allowed to do or to use is the fact that it's true for n equal to k, right? So we know that for the first k this holds, and we need to show that it's true for the next one. And here you can see, let me color this here. Oh, let me color this here. Here you can see that the first k terms is appearing. And so by the inductive hypothesis, so this here is called the induction hypothesis. So by that, it follows that that first part is equal to k plus 1 over 2, and then plus k plus 1 just itself. Okay, so we know by the inductive hypothesis that this is true. Now, this is, you can multiply and divide by 2 here, and you factor out, and this will give you k plus 1. So you factor out the k plus 1 here, and you get k plus 2. K plus 2 divided by 2. But this is exactly this expression here for n equal to k plus 1, right? So when n is equal to k plus 1, you get k plus 1 here, and this part is k plus 2 over 2. So we just showed that if this is true, so if the statement we want to prove holds for k, then it must also hold for k plus 1. And once again, since it holds for 1, then that means that it holds for 2. And then since it holds for 2, together with this, it holds for 3, and so on. And so with this, so by induction, the formula the formula holds or is true for all positive integers n.